Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I want to thank each and every one of you for joining me today in our webinar to talk about the outstanding new features of AFT Impulse version 9. You're in for a great time. It has to be because it rhymes, right? Anyway, I hope that you all are doing very well and are having a great week and a fine morning, afternoon, or evening, wherever you are located around the world. So thanks again for joining me. All right. So AFT Impulse version 9 was released very recently, and time is going by fast. I can't remember what day it was released, but anyway, I'm excited to go over some of the new features and capabilities with you all. And so without further ado, let's get into it. AFT.com is our website that you all know and love. And I want to take you to a page that is maybe not the easiest to find, but if you went on our website to aft.com/AFT-impulse-historical-new-features, then what you're going to be able to find is a entire history of all of the new features that came out for each version of AFT Impulse. And this is really handy because you can see the progression of how the software has been improved over the years. And so I'm going to go ahead and copy this link. And for those of you who are listening in live today, you will be able to have the link. If you are listening to the recorded version of the webinar, then be sure to pay attention to this URL, and that way you'll be able to find the key historical new features. And Fathom and Arrow also has a page for historical new features. You would simply replace the word impulse with Fathom or Arrow, respectively. And so if you were to scroll down, you can see the significant new features, and then you can see more details down below. So this is all the stuff that came out with Impulse 9. These are the features with Impulse 8, 7, 6, so on and so forth. And I want to remind you that if you happen to have a very old license of AFT Impulse and it was purchased as a perpetual license, not a lease, if your support agreement has expired, you can reinstate that so that you can get tech support again, which is critical for AFT Impulse. But when you get upgraded to the latest version, you're not only getting the new version features with Impulse 9, you're also getting everything that came with Impulse 8 and 7 and so forth. So this might be a page that you want to keep an eye on so you can just monitor the new features that we've come out with over the years. So I'm going to go ahead and set that aside, and we're going to get into AFT Impulse 9. Give me 1 second. All right. So there's a handful of new features that are more generalized to all of our software that came out in the latest version. So for example, there are going to be features that you see in Impulse 9 that also came out with Fathom 12 and Arrow 9. And really, that's one of the beautiful things about our software is that when you learn one of the software tools, you already know how to use the other ones. There's cross knowledge you can take advantage of there. So let's take a look at some of the things that are new. The very first thing that I want to highlight is the analysis setup window. And so if you remember in previous versions, the status light is typically what you would click on in order to begin building your model and whatnot, because it will guide you through the model building and definition process. And it still does. So when you click on it, it pulls up our analysis setup window, And really what this is that we have taken several of the windows that you would find throughout the software, and we consolidated them into a single window where you can access everything all at once to help minimize some clicks, as well as constantly having to get in and out of various windows. As you notice, you've got your fluid properties, which is your system properties, your pipe sectioning, your transient control, your force definitions, etc. All of those are consolidated into a single window now. And one thing I want to turn on here is our blue highlighting. There we go. And so let me go back into the analysis setup window here. So with the light blue highlighting, that indicates required input. And let me back up one further step before that. When you first open up the analysis setup window, what you want to look at first is the pages that have an exclamation point. So you have an exclamation point here for fluid properties. That means that you have to do something in this panel. And where you see the next check mark is, or your exclamation mark is for the fluid itself. So that's what you need to do, is define your fluid, and a user specified fluid, the minimum input is density, viscosity, and bulk modulus. And so that helps guide you with not only the exclamation points, but also the blue highlighting. And then if you choose AFT standard, it's a little bit easier because all you need to do is just type in a temperature and then it calculates everything. And then once you're done with that step, it's going to automatically put a green circle with a check mark next to that item, meaning that you're done with it. Now, anything else that you don't have a exclamation point or anything else beside it, those are things that the default definition will solve the majority of the cases for you. For example, your viscosity model is most likely going to be Newtonian. And so that way, that's one less thing that you would have to go in and specify. You can do constant variable fluid properties, laminar flows, etc. Now, sectioning is going to require that you have pipes defined on the workspace and a functional model. And so this webinar is not to go into the details of how to section your pipes and how to section them effectively. I'm just demonstrating this is where you're going to find the window now, is right within the analysis setup menu itself. All right, and then we have output pipe stations. A little bit of a background with the method of characteristics, with how Impulse solves a calculation for a pipe. Let's say here that we have a pipe going along, and we have our inlet at the beginning right here and the outlet. And so in order for Impulse to capture the surge and water hammer waves, it has to break this pipe up into bits that we call pipe sections. And so it just divides the pipe up into all these bits, and wherever you have a division from one chunk of pipe to the next, this is called a computation station. So the computation stations will divide a chunk of pipe, and the chunk of pipe itself would be this portion right here. That's called a pipe section. And so a pipe section has a volume associated with it versus a computation station. This is simply a mathematical point where we are doing the calculations. And so here we have several computation stations and several pipe sections. So the reason why I bring this up is because when you're doing your water hammer analysis, there can be a lot of stuff that is happening at these interior pipe stations, and you're going to want to know what's going on inside the pipe. By default, when I go back to the screen in Impulse, you're going to see that we're only going to save the results in the output for the inlet of the pipe and the outlet of the pipe. No other stations here are saved to the output file unless you tell Impulse to save these intermediate pipe stations. And it's really important because if you want to pick this particular pipe station right here and you want to plot the pressure versus time so you can see what's happening at this particular station, you need to make sure that you include that station's output in the output file. So be sure to keep that in mind when you are dealing with your water hammer analysis in Impulse. So when we go back to this tab right here, output pipe stations, this is where you can choose which specific computation stations inside of a pipe you want to save to the output file. What I highly recommend to all of you is to simply click on the All button. That way it checks the boxes for all of the pipes here in the list. And then simply click on this button right here that says change the selected pipes to, and make sure that this says all stations. So when I click on this, it's going to save the results for all piping stations for all the pipes that would be in this list right here. And yes, it will increase the output file size as well as the runtime, but I would rather deal with a longer runtime and a larger output file size at the beginning to be able to have a better handle on analyzing my results. So this is my suggestion, to always save all of the stations for all of the pipes and just deal with the longer runtime. So that is something I think that is important with that particular window there. You can also choose the junctions to save their output. There's no junctions in this model, obviously, but pumps, valves, control valves, gas accumulators, surge tanks, those are junctions that their results can change over time for their junction specific parameters, like the pump speed for a pump, and you'd want to be able to plot that versus time. And so this is where you would choose to save your various junction results in that window. Now let's get into the transient control area here. The transient control, this is where you can choose what time simulation mode that you're dealing with. It's a good idea whenever you're doing a water hammer analysis to first run your model in steady state mode. Get a sanity check for what your system pressures and flow rates and velocities are, and that way you can make sure that the model is functioning correctly. And then once you're done with that, then you can move on to doing transient mode. Now, I want to point out that steady only, this is not intended to replace a steady state simulation that you can do with AFT Fathom. This is a very basic and robust steady state calculation. It's for the cases where the vast majority of your work is dealing with water hammer situations where you're going to be doing surge analysis for the most time. So if you didn't want to take a look at getting Fathom, this would be helpful if you only need to do a quick steady state calculation every once in a great while. Keep in mind that you're not able to do pump and system curves in Impulse or heat transfer, cost calculations. There's several other things that are available. Also, there's additional profile plot graph parameters that are only available in Fathom for steady state, not in Impulse. So keep that in mind. This is just for doing a quick and dirty steady state calculation. This is where you define how long you want to run your analysis. And then in addition to saving each individual computation station, like how I was doing earlier, it's also important to save your output to the file, which will obviously happen. I recommend still keeping it every time step. You can skip time steps if you want, and that will help reduce your output file size and your runtime, but not by much. The reason why is because the biggest impact on your model runtime is going to be all about sectioning. And so sectioning is going to always play the biggest factor in longer runtimes. Now, I'm not going to go into great detail about it, but something that I want to highlight is our tips and tricks page. So if you go to our website, aft.com, under the Learning Center, and then tips and tricks, there's a particular article that I want you to look for. And if you click on the magnifying glass right here, you can do a keyword search. And let's do a keyword search for "you should combine your pipes." So this is where you can find a blog article that I wrote a while back, and not too long ago. Feels like a long time ago. But anyway, this talks about effective strategies for pipe sectioning, where you might be tempted to model every single component and minor loss explicitly because you think that it gives you more accuracy. Well, the thing is, you could lump in all of those minor losses into the pipes themselves, and when you go to read through this article and you take a look at the results in my analysis, the results are virtually identical with each other for the two different situations. So a lot of times you can get away with lumping your minor losses into the pipes themselves rather than having to use junctions. Now, on that note, in this article, you'll see here that I have these general components being used to simulate elbows. And so one of the new features that came out with Impulse 9 is some additional junctions that you can work with now. And so let me cancel out of this window here. You now have the ability to work to use elbow junctions, orifice plates, venturis, screens, etc. Those are some new junctions that you can throw into your model. One of the reasons why they were not available in previous versions is because users would be tempted to use them if they're there. And so, they would run into a situation where, they have all of these, if elbow junctions were available, they would have all of them explicitly modeled and all of these really short pipes, and that would lead to dramatically long run times, which are completely unnecessary. And so, effort to try and help encourage users to use the software intelligently and understand how to section their pipes properly, which you'll learn about in this blog article. The ability to model just every single junction like you can in Fathom was not there. But upon popular request, people still wanted to be able to model all of their elbows and orifice plates and stuff like that in their impulse models, and so we added them in, and you're more than welcome to use them. And I would encourage you to do your own sensitivity analysis. Build a model, something like this, where you include all of your various junctions that you have in your model explicitly as junctions with additional pipes, and then combine them where you're lumping the effective losses of those minor fittings into the pipes themselves, and then compare your results to each other, because you're going to see that the results are going to be very similar. In this blog article, the results are actually in this separate PDF here, which should be downloadable. Let's see. Yeah, you can click on the arrows and download it. We can open up in a presentation mode, and as you can see here, I have. Let me see if I can zoom in. It's not letting me zoom in, but as you can see, I have several different cases here, and look at that. The results are exactly right on top of each other. No differences. There's only some slight differences when you're looking at the elbows themselves, but for the most part, your results are going to be just about exactly the same. So these are also the force sets that I defined in that. And the force sets are the same. So if force calculations are really important to you, which I imagine they are, you don't have to have every single pipe and junction explicitly modeled in order to have accurate force calculations either. You can lump those in as additional fittings, and based upon how your pipes are sectioned, Impulse is going to handle that, and your force calculations will be virtually identical to where if you were using junctions themselves. So let me go ahead and copy this article, and I'm going to paste this all to you in the chat window that are listening in live to the GoToMeeting. For those of you who are listening to the recording, again, go to our tips and tricks page and simply do a keyword search here for "you should combine your pipes," and you'll be able to find that article. Another thought is that orifice plates can potentially be a reflecting point for transient water hammer waves. And that is true, but the question is, how big is the actual effect? And so if you have a pipe with a orifice right here, and we have something that looks like that, and then downstream we have a valve, and we're doing a transient on the valve where we're slamming it shut. And so when we slam that valve shut, we're going to see an increase in pressure at the valve, and that's going to transmit upstream of the valve. So the thing is, when this pressure wave, we'll just draw that to show a wave, when this is oscillating and transmitting through, we have a restriction right here where there's going to be a partial reflection of a water hammer wave that goes backwards towards the valve while we still have a propagation of wave through the rest of the piping system. And when we have that effect, the waves right here that are being partially reflected are going to interact with what's going on right in here. And that can add sometimes some constructive or destructive interference patterns that can really make that oscillation quite complicated. And so you can analyze that with your orifice plates now, but I would again recommend that you do your own sensitivity analysis first, because more often than not, the impact of your restriction in your orifice plates on the wave reflections that would happen very well might be quite minuscule, and it may not cause that big of a difference in results. So same thing, build a model where you use your orifice junction and then duplicate it where you throw that orifice into the pipe itself as a fitting, compare the results, and that'll tell you if you should actually be modeling your orifice plate explicitly or not. Okay, let's go into a couple more things here in the analysis setup window that I want to point out. Transient cavitation can be defined on a new tab here, whether you're doing discrete vapor cavity model or discrete gas cavity. Transient friction, This is a important one here where this can allow your friction factors to change during the analysis. And there's a few different modes. Constant is going to use the same friction factors that were calculated during the steady state run, and it's going to use them all throughout the entire transient analysis. If you switch it to time varying, there's two options. There's simple, and then there is advanced. And so using either of these options here for time varying, that's going to have a decently significant impact on your runtime. In the past, we've seen it impact your runtime by a factor of 3, but we have implemented some new methods to try and get the solver to be able to run faster. So it may not be that much of a impact as a factor of 3, but again, do your own sensitivity analysis. Again, I'm going to take you back to our tips and tricks page, and another keyword search is variable resistance. Excuse me. So this was another article that I wrote a while ago called "When Should You Use Variable Pipe Resistance?" And in this article, I show you some big, very scary red warning messages that might cause you alarm to where you would think, uh-oh, I better use variable pipe resistance like it's telling me to. Note that this is in one of the previous versions of Impulse. That's why it looks a little bit different. But the fact of the matter is, just like modeling your junctions explicitly versus including them in the pipes, this may not cause a very big difference in results. As you can see right here, I have with and without variable resistance, no differences in results there. It has a bigger impact if you're doing a startup simulation, where initially, if you have no flow in the pipes, your friction factors are going to be much higher. And if you use those same friction factors in the transient portion as things come up to speed, then those are going to be large friction factors with a little bit more significant pressure losses. But the reality is, it may not cause a very significant difference in results. And as you can see in my analysis, it doesn't. The results are virtually identical. So what you can do is read through this article, which I'm chatting to you again here in the GoToMeeting chat. And then when you do your analysis, take it one step further. Do constant, and then do simple. Simple is the previous variable resistance option that you would see in the blog article there, and then compare it against the new one, advanced, the unsteady Bernoulli equation. And so this option here actually does do a good job of where it dampens out your pressure waves a lot faster. So this option very well might show you some very significant differences than what you've seen in the past. But again, I encourage you to take a look at that. You can define your forces here on the force definition page. One thing I want to mention about the non-Newtonian fluids, that's where it is. If I can click the right one here. So we implemented a new non-Newtonian viscosity model, which is the Herschel-Bulkley model. And so Herschel-Bulkley is, from my understanding, used a lot in the water and wastewater industry and probably some other industries that I may not be directly aware of. But we've also redesigned the viscosity model window a little bit, because when you're choosing these different options here, it's going to highlight what that type of non-Newtonian model looks like. So here's your Newtonian behavior, and this is what power law would look like. You're going to have no yield stress, but you're going to have a non-linear viscosity relationship. If you did Bingham plastic, oops, I choose the wrong one. Bingham plastic here shows that it's going to be linear like Newtonian, but you have to overcome some yield stress to get the fluid moving first. And then Herschel-Bulkley combines both of them basically, where you have that yield stress that you have to overcome and you have the non-linear relationship. And if you calculate from rheological data, you can do different raw data types. And for Herschel-Bulkley, it only brings in shear rheometer data. But if you were to choose one like power law, you can specify if your data is from a tube viscometer or a shear viscometer, which would be inside of a pipe, I believe, or tube viscometer. Well, no, maybe this is a spinning viscometer. I'm not an expert on viscometers, so you can do different options there. All right. So enough about that with the analysis setup window. A new feature that is implemented into valves, which is really helpful for Impulse, is in the past, you would only be able to specify CV versus time transient profiles. Now, you have the option to model open percent versus time. So here, you can change how your valve is going, or you can specify how your valve is going to change on an open percentage basis. This is useful if you don't know how the CV changes itself. Now, obviously, for using this option, you're going to have to go to the optional tab itself and then specify a open percent versus CV table. So when you specify your open percent versus CV table, that's where you will be able to then go in and model your open percent versus time transient profile for the transient tab. All right. One more general thing that I want to talk about here with AFT Impulse is the new library format. So previous versions, we would call them databases. Well, now we call them libraries because database would sometimes have a different term meaning for different people. And a better term for it is a library, where you're basically just storing your custom information in a library so you can easily access it later. And basically what we've done is something similar to the analysis setup window, where we had a whole bunch of different windows previously, and we went in and consolidated them to make it a little bit easier to use and to navigate, as well as making it a little bit easier to access external database files and share that custom information. So this is where you can get more details about the, or this is where you can use the custom information in the library manager. Custom pipe materials can be built in this panel here. Custom fluids can be built in this panel here, etc. Now, one thing that I really like is that our software, let me go back to our website. We are using a brand new help system, which is web-based, and it's available on our website. So now you don't have to actually be in the software to be able to have the ability to read through our software documentation. You can navigate to it by going to the support menu and then down to help documentation, or you can simply click on this button right here, which takes you right to our help site. So this is also advantageous because if you don't have Fathom or Arrow or Extreme, but you want to learn more about them, you can access those help files also. And you can even scroll down and you can look at the examples section here, and you can read through these examples, the tutorials here. You can see the results in the documentation. You can also look at the verification cases, and you can see how some of the, one of the methods that we have used to verify that the software calculations are correct is by all of these different verification cases. So Impulse, you have the same sort of setup. So here's the AFT Impulse help site, and you can access the walkthrough tutorials down here. If you don't have the Impulse modules and you want to learn a little bit more about how they might be used, you can access the module examples, and you can learn about how the settling slurry in Impulse can be used, or pulsation analysis. And of course, our verification cases, which are really important for AFT Impulse. So we've got several verification cases here, like we do in Fathom. On that note, with regard to AFT Impulse, if you go to the top on the overview of AFT Impulse, here's where you can see what's new specifically in version 9. So you can go back, to learning, okay, what was that analysis setup window? What's all going on in there? And how do the libraries work? This will take you right to that help file so you can start learning more about how it works. And you can also see some screenshots to get a better idea of what the new features look like. And it also provides documentation for the last 3 versions, which I think is really helpful because, Impulse 6 came out with a lot of really important new versions, and you'd want to be able to see what those are. Same thing like Impulse 8 with our scenario comparison tool. You can go directly to that topic in the help file and read about it. So be sure to check that out as well. All right, so now let's go ahead and get into one of the other models that I already have pre-built to go over some Impulse specific things. And what I want to talk about first is the improvements in graphing, the graphing capabilities. And so one of the approaches when you're doing your water hammer analysis is to, where sometimes you might need to change the pipe sectioning. So let's go to this example right here, this scenario. In this scenario right here, we have, I have 2 cases where I have one pipeline and a second pipeline. What in the world is going on? Well, I have a pump where I am doing a pump trip from the beginning of the transient simulation. So as the pump trips, the fluid is going to want to flow downhill, and I have a valve that is representing a check valve to prevent that from happening. So here's how I set up my check valve. It's actually a regular valve using check valve logic. So here I have a transient defined, which is a dual event cyclic. So I have 2 events that can happen. Initially, this valve is open because we're pumping water up the hill. That's our normal operation. So the first event would be to close the valve. And I'm going to close the valve in a quarter of a second based upon a velocity in a pipe. So if the velocity gets to be less than or equal to 0 at the inlet of pipe 3, which is right here, that's going to close the pipe. I have a second event, which is going to reopen the check valve. So this is going to reopen in a quarter of a second, and that will only reopen if I have a pressure difference across the valve itself greater than 2 psi. So if the pressure difference across the valve is greater than 2 psi, that will trigger this event to happen. And these 2 events can cycle with each other. So that valve can open and close, open, close, open, close, open, close, however it works out. Now I have a gas accumulator. And so this is the old-fashioned input of modeling my gas accumulator, which is a very simplistic approach. I'm simply specifying a known initial gas volume inside my accumulator. The polytropic constant for air is about 1.2. You can specify a short connector pipe right here, and that's how I have things specified. So I have compared a situation where I want to see what the effects are if I ignore the gas accumulator. So if I have no surge suppression device, I can simply go to the optional tab and say, hey, just ignore it. Pretend it's not there. That causes it to simply act like a branch junction where it's literally doing absolutely nothing. And so this is where you can see, is your gas accumulator going to do a good job at dampening out the pressure surge waves in your system, or is it going to cause more problems? Which there's a possibility that that can happen. Um, if you were to read through in the help file on this example, I want to refer you to uh, the pump trip with accumulator example here. So this is where you can essentially build the model from scratch that I am demonstrating here today. I've only made some slight modifications. In the example model lumps a check valve inside the pump. I don't like doing that, and I don't recommend it because that can cause your check valve inside the pump to open and close instantaneously and cause a lot of chatter, which is not realistic. It's going to take some finite amount of time to open and close. And so I don't like doing that. Instead, in my model, I modeled a check valve explicitly. Let's see, where is it? I modeled the check valve explicitly with a regular valve. You can use the check valve option, but with that, you're going to need a lot more data because we have enhanced the check valve junction to be able to do better check valve calculations for swing check valves and nozzle check valves with doing force balances inside them. But if you don't have any of that data available, that's not going to be the greatest check valve to use. So instead, I am using a regular valve with check valve logic in that case. And so that's one of the modifications I've made. So you can do this same analysis that I'm doing by reading through the example, and you'll get pretty dang close enough. And you can also see for yourself what the differences are between using an accumulator and not using one. So in this scenario right here, if I go into my analysis setup window and I look at my pipe sectioning, we can see here that I'm using one section in the controlling pipe. So if we scan down this list here, we can see that the shortest pipe in the model is 10 feet long and the longest pipe is 940. So that's not a huge difference. And so I might want to take a look and see what happens if I put two sections in the controlling pipe. And I did exactly that. So here's my scenario with two sections in the controlling pipe. And when I open up the sectioning window here, we can see two sections. So that means there's going to be two sections in this 10-foot long pipe that are 5 feet long each. Now, this is not necessarily giving you more accuracy, it's just giving you more resolution on the results of what's going on. So as you can see here for this longer pipe, we do have a lot more sections and a little bit longer of a runtime. How big of a difference is this really going to cause on the results? Well, one of the great enhancements with Impulse 9 is when you are doing your multi-scenario graphing, you can compare scenarios that have different sectioning characteristics, which is awesome. So if I go to the graph results window here and I do my profile plot, I'm going to click on the plot single path because I already created some groups and that just makes it a little bit easier. And I'm going to plot the flow path with a gas accumulator. And I'm going to click on the multi-scenario tab or drop down rather, click on select scenarios. Which ones do I want to compare? I want to compare the original with one section versus two sections. Click OK. And this is the reason why I highly recommend saving all stations to the output file. So again, where are we doing this? If we go to the analysis setup window under output pipe stations right here, this is why saving all stations is so incredibly important. Simply because it gives me the ability to use this option, the output file rather than the solver. Why do I like the output file itself? Well, very soon you're going to see why. So here's my profile animation. And as we play this, our pump trip has started and both systems are dropping their pressure at about the same time. Now, keep in mind the flow is dropping too, and then once that check valve closes, that's going to cause a bunch of transients to start happening in our system. Now, let me speed this up a little bit. This is why I really like to use the animate with the output option instead of the solver. It's because when results start to go haywire like that, and there's a whole bunch of chaos, that happens way too fast for you to be able to really see what's going on. So I want to be able to pause the animation and then back up time steps. So I can back things up to the point right before all of the chaos happened. You can also hold your mouse button down on that minus sign to keep going backwards. You cannot do this when you are using the solver option. That's why I don't think it's very helpful. It allows you to have a shorter runtime when you first run your model if you're not saving all stations, but you don't get as much benefit when you actually go to analyze your results. And so when I keep backing up here, I want to get to the point right when that check valve was closing. Let's see here. So do default speed. Go forward a little bit. This is a nice way to be able to easily see your results as well. Well, anyway, I think you get my point. It gives you a lot more flexibility when you're analyzing your results there. So here, the only difference between the two models is the section. There we go. So now I can back up just like this. And so this is right before that check valve closes, which is right here. So we can march forward another time step. Then now we can see where it starts to close. And so here, if you watch the blue line, that's with two sections. It starts to close faster and surge faster than the other one. But as we watch things go by in time, some of the pressure spikes that are in the one section scenario get to be a little bit larger than the two section scenario. And so this is why it's really helpful to be able to graph your different scenarios that are using or that are using different pipe sectioning. And so if I just simply did a transient graph of the pressure at the pipes, let's take a look at that. So this is one scenario. If we compare this to the one section scenario, oh my, look, there's a really big difference there. So when you break things down, the inlet of the check valve looks like that. When you only have one section in your controlling pipe, if you put two sections, wow, that smooths it out a lot. Why such a big difference? Well, maybe there's cavitation going on that is causing a lot of that chaotic behavior. And adding another section in allows a better smooth analysis of the results. Same thing here with the downstream end of the check valve. So now you can compare different sectioning scenarios, and I just think that that is wonderful. All right, let's get into the new and improved gas accumulator window. So as you can see, I have several families of scenarios. I have a vertical tank option where I'm trying different sizes, and then I have a horizontal tank option where I'm trying different sizes. So let's take a look at that. In the vertical tank option, give me 1 second here. All right. So this is where you can get a lot more flexibility and realism of your gas accumulators. And so here, if you check the box for your tank geometry, this is where you can get more realistic with your actual gas accumulator. So here you would choose your tank type. Are you dealing with a vertical tank or a horizontal tank or some other weird geometry like that? If you're doing this option, what you're going to be specifying is what your accumulated liquid volume is as a function of height inside that. And so that might be kind of complicated to figure out, but it can be done, and that's how you would do it. So let me click cancel. So in this family of scenarios, I am using a vertical tank option, and then there's the cap type. So we have different cap types. You can do spherical, semi-elliptical, flat, different ASME types. And the reason why is because those will change how much volume you have inside the cap, and that gives you a little bit more accuracy there. The reason why I keep clicking cancel is because one of my biggest tips that I always recommend is if you are doing anything in a window that you're not intentionally actually changing, never click OK, because you might accidentally accept changes that you didn't intend. So even if you're just going in here to look at something, when you leave that window, click the cancel button just to prevent any accidental changes. So a little tip there. Here, I'm just keeping it simple using a spherical cap type, and you can choose what field you're calculating. Either do you want it to calculate the volume or the height or the diameter? So here, if I did height, then I need to specify the volume. And when you click on any of these fields, it's going to highlight that area. Diameter, it highlights that dimension. If I do volume, there's my height and there's my diameter. So when we look at this, I'm keeping the height the same in all of these scenarios, and I'm changing the diameter. So I'm changing the diameter from 6 inches to 24 inches in these families of scenarios. Now, I'm also pre-charging with the known amount of gas inside the accumulator, and I've got a short connector pipe. All of that, none of that is new from previous versions. So I can cancel out of there. And in the horizontal tank option, well, it's a horizontal tank. But similarly, I'm keeping the length the same, as you can see here, and I'm changing the diameter. So I'm going from 6 to 24 inches just like before, but we're laying the tank on the side. Why in the world is the tank geometry so useful? Well, you might have better data about that to get a better picture of how much volume is inside the tank. But a new capability is you can actually track the liquid level inside the accumulator. So you can see how high up and down it goes during a transient simulation. So that is pretty spectacular. So I've already ran all my scenarios, and so there's something new where if you're doing a batch run of multiple scenarios at a time, you have the option to run your batch run in the background. And that's helpful because you can then pull one of your other windows up front and you can do your other work while you're waiting for all of these 10 scenarios to finish converging, which for Impulse could take several minutes. So that is a nice feature and capability. Something else that is new with relation to caution messages and warning messages is at the end of your analysis, when you're doing your batch run. I took a screenshot of it yesterday because I don't want to run all these scenarios again for you. But when you finish running your batch run, this is going to give you information about what happened in each scenario. So as you can see here, it tells me this scenario had 4 warnings. I didn't specify any design alerts, so nothing is being exceeded there. And it tells me which scenarios have warnings, and that way I can go in and examine each of those scenarios individually. So that's something new that it tells you is what scenarios have warning messages. Now let's plot some things together here. So let me go to this particular scenario for the vertical tank. And I'm going to go to the Graph Results tab. And let's take a look at the gas accumulator volume. And let's look at all of our different scenarios. Let's do the original accumulator and then the other vertical tank ones. And let's plot that. All right, so here we've got everything plotted together. So here is the original gas accumulator that we looked at in the previous scenario, where we're not doing any special tank geometries, we're just specifying volume, and that's it. Well, the 6-inch diameter accumulator that's 4 feet long, or 4 feet high rather, looks like this, where here is how much gas I have inside, and then that gas depletes, and then it levels out. And then, oddly enough, when we look at the other accumulator options, they are matching the original accumulator a lot better and a lot more closely. So pretty much that's telling me that this 6-inch diameter accumulator is not going to work. Any of these other options would be a better pick. And now there is a lot of craziness that is happening in that 6-inch scenario that I don't have a full hand on. But the good news is that this webinar is not about evaluating those results. It's showing you the new capabilities of doing the different geometries and how you can plot the results together. I can also add on the liquid level. So here is the liquid height. Inside the accumulator. Now you just have to give it some time because it is literally plotting tens of thousands of data points on a single graph. So patience is key. And so here you can see how the liquid level changes. The original accumulator, that is at 0 because, well, there's no geometry that dictates how high that liquid level gets. So we can just ignore that. Now, for the smallest accumulator, you can see here that basically that liquid level drops really quick, and there's some weird cavitation going on there, and you can see how it tends to burp a little bit here, and so that's not a very good accumulator to use. But then you can see how the other accumulators do a lot better. And so, this is in feet. Maybe it's better to look at this in inches, at least, especially when we look at the horizontal ones. And then we can add another for liquid volume. So if I want to look at, let's see, liquid volume overall for gallons, here's how many gallons of liquid inside the accumulator is changing over time. Again, it's plotting tens of thousands of data points there. Perfect. And so here we can see how the liquid volume changes in terms of gallons, and that might be something that is important for you to know. Now let's compare the vertical tank scenarios. I'm going to compare these three with these three. And we're going to see how different those results are. So let me change this up a little bit. I'm going to uncheck that one, and then check these three. I tell you, that multi-scenario graphing is absolutely amazing. And if you're not using it, well, you definitely need to. Fathom and Arrow can also now do multi-scenario graphing as well. Now, the interesting thing that we want to look at is, how different are those results going to be? Because when we're using the same diameter and lengths, this actually gives the same amount of volume inside the accumulators. So here, that explains why the volumes are exactly the same for the change in volume inside the accumulator, or you can also plot the change in pressure. But here's what's different, is you can see clearly how the liquid heights are much lower. If you one thing that's useful is if you right click on the legend, you can show the full scenario path. It's supposed to. That was working earlier when I was looking at it. I'm not sure why it's not working now. Anyway, you can see here that this is for the horizontal tank, so that liquid level is a lot more modest compared to the vertical tanks. And then you can see how the liquid volumes also change accordingly, which happen to be exactly the same. So that's the 12-inch by 4-inch, 18 by 4, 24 by 4. So volume is staying exactly the same. Okay, well, that is basically it that I wanted to demonstrate for you all today in the webinar for the new features for AFT Impulse 9. Thank you very much for your time and your attendance. And if any of you have any questions, feel free to get into contact with us, and we'll be glad to help. Take care, everyone, and have a wonderful rest of your week.